Everyone, and thanks for watching Edupedia World videos. In this session of atomic structure, we'll talk about the topic of atomic orbitals. So we have already seen the basic of atomic orbitals. Now we'll go into the details of them, different atomic orbitals, their shapes and their significance. Right. So let's start with what atomic orbitals are. So basically, atomic orbital you can say is the home of electron. Okay, that is where the electron ultimately resides. So atomic orbital means it tells you the location of electron, obviously the probable location, not the exact location, and it also gives you the energy of your electron. Alright, so atomic orbital is going to be the most crucial thing that we'll study after this, okay, in quantum atomic model. So what do I mean by home of electron? It means that probability of finding the electron in that region, okay, of space is more than 90%. If you remember, in quantum model, the electron can be present anywhere from origin to infinity. Alright, so what is the region where it is likely to be present most? Okay, and what are the regions where it is least likely? So this we will identify on the basis of study of atomic orbitals. Alright, so atomic orbitals are the regions where probability is very high, okay, and very high can be defined as greater than 90%. You can also define it as greater than 95%, but for now let's go with 90%. So they are represented by quantum number small m. Alright, we have already seen this. It is called magnetic quantum number, okay, and what we have also studied before is that the shape of atomic orbital depends on the quantum number L, that is the azimuthal quantum number. Okay, so the orbital itself is represented by small m, but its shape is determined by small l. Alright, so one by one let's look at different orbitals which we have to study. So these are the orbitals which we'll be studying. Okay, here on the left hand side, okay, this is L, the value of azimuthal quantum number for various orbitals. This is the value of m, that is the magnetic quantum number or the value of orbital itself, you can say, and this is the shape of the orbital, okay, that is in 3D space what kind of shape the region of electron will have. Okay. So first let's talk about the s orbital. Okay. So see, now the value of n, that is the value of shell, can be 1, 2, 3, anything. Alright, okay, but once you have fixed this n, the shape of the orbital depends entirely on the azimuthal quantum number. Okay, and s orbitals have azimuthal quantum number value of 0. Okay, this is always fixed. Whenever L is equal to 0, the orbital is s orbital. Alright, so for whether the n value is 1, 2, 3, it doesn't matter. As long as it is s, the L will always have a value of 0. We know this. That means 1s, 2s, 3s. They will have similar kind of, okay, and so on and so forth. Alright, they will all have similar kind of orbitals. Okay, so let's look at their magnetic quantum number. Okay, so this magnetic quantum number for s has only one value, which is again 0. And its shape is spherical. That means all s orbitals in the world, they all are spherical in nature. Okay, so they are like 3D spherical balls. Okay, it's like your cricket ball or your tennis ball, something like that. Okay, so whether it is 1s, 2s or 3s, they will all have spherical shapes, or 4s, 5s, any s orbital will have this shape. Okay, then there is p orbital. Okay, once again there can be various p orbitals like 2p, 3p and so on. So for all p orbitals, the value of azimuthal quantum number is always 1. Alright, so L is equal to 1 means the orbital we are talking about is going to be a p orbital. Alright, the magnetic quantum number can have three different values: -1, 0 and +1. Okay, that is to say, for P, okay, or for L is equal to 1, there are three different orbitals present. Okay, so what are their shapes? All of them will have same shape. Okay, all these three orbitals, the one represented by -1, 0 and +1, all these three all will have same shape, called which you can define it as a dumbbell shape. It looks something like this. Okay, that is the dumbbells, you might have seen them before. Okay, it's like you have a stick with two lobes, okay, on the two sides, which you use for weightlifting. Okay, so it's something like that. Okay, you have two different lobes. Okay, these are called lobes. So you have two different lobes over here. Okay, we'll go into the details of each of these orbitals in subsequent slides. Okay, then there is d orbital. Okay, now for d orbital, L value is always equals to 2, and there can be 5 different m values. That means d, where for L is equal to 2, okay, the orbital is always d, but it has 5 different orbitals in it. Okay, with values of -2, -1, 0, +1 and +2. Okay, they have, most of them have double dumbbell shape. Okay, not all of them. Will look into the one which doesn't have the double dumbbell shape. So that shape looks something like this. Okay, so instead of one dumbbell, that is, instead of one dumbbell will have two lobes. Instead of one dumbbell, you have two dumbbells, which means you will have, okay, this is one dumbbell, so two lobes, and this is another dumbbell, so another two lobes. So two dumbbell or double dumbbell means you will have 4 lobes over here. Okay. Then there is f orbital, for which L value is 3, m has 7 different values. Now they have a lot more complex structures, so we won't be able to draw them or study them over here, and we don't even have to as per our syllabus. Okay, and it doesn't stops at f, right? It goes on further. Okay, and the shapes and structures become more and more complex. So we won't go into all that, but we'll study S, P and D in great detail here. So what is the significance of orbital? See, first is they decide the spatial orientation. As you have seen, S has only one orbital, but P and D have different orbitals in them. Okay, P has 3 different orbitals, -1, 0, +1. So how do we differentiate between them? Okay, so each of them has a different spatial orientation. Alright, so though their shape is similar, they have different alignment in space. We'll look at those alignments, okay, in a few minutes. And there is another concept called degeneracy. So for now, let's take degeneracy as orbitals having same energy values. Okay, so if you have, say, randomly 2 different orbitals in space, okay, for a particular atom, okay, not 2 different atoms, for a particular atom, if 2 different orbitals have same values of energy, all right, then those 2 orbitals will be called degenerate orbitals. We'll look at degenerate orbitals. Okay, and when they don't have same energy, you can say they are non-degenerate. Okay. So orbitals explains us these two concepts very well. So first let's look at s orbital. So s orbital is completely symmetrical, okay, and it has a spherical shape. That is, it's just like a 3D ball in space. Okay, so starting from origin, all right, no matter which direction you go in, okay, it looks same. That is, it is completely symmetrical. All right, so if you go along any radial direction, the probability of finding electron will be same if you go equal distance from the nucleus. Okay, see, you must understand all these orbitals, they are not like solid shapes. Okay, they are not like solid walls in which electron is contained. The orbital itself is made up of electron cloud density. Okay, so when we are talking about the shape of orbital, we are actually talking about the shape of electron cloud density. Okay, so how is that s orbital has a spherical shape? Because the electron in an s orbital, okay, moves in a yep. So electron in an s orbital moves in a spherical region. Okay, and because of that, the electron likelihood of finding electron is in a spherical region. Okay, and that is why we say that s orbital has a spherical cloud density. Okay, or it has a spherical shape. So it is not solid walls. The shape itself is made up of electron cloud density. That is, electron can be at this point. Okay, electron change can suddenly change and move to this position, then it can move to this position, this. Okay, so the positions which it is likely to occupy will have spherical shape. All right, it is non-degenerate. Okay, so see, all s orbitals have only, okay, one m value, which is m equals to 0. So that is, you cannot have two different s orbitals with same energy, because there is just one s orbital, right? So 1s is one of them, the second shell will have another s orbital, third shell will have another s orbital, and so on and so forth. All right, so what is the difference between 1s, 2s, 3s, 4s? Okay, so they all have spherical shape, but their sizes differ. Okay, so as you move from 1 to 2, from 2 to 3, and from 3 to 4, and so on, the size keeps on increasing. Okay, that is, you can say the radius of this sphere keeps on increasing. That is, the likelihood of finding the electron keeps on increasing away from the nucleus. All right, so 1s, the electron in 1s will be more likely to be present near nucleus, and that in 2s will be a bit further from nucleus. In 3s, the electron is more likely to be found even farther away from the nucleus. Okay, so that is the only difference here. There is a difference of size. Okay, and later on we'll see there is also a difference of energy. All right, so for now, just remember that all have same shapes but different sizes. Next we have p orbital. So p orbital has three different m values. Okay, so m is equal to either -1 or 0 or +1. Okay, so see, now there cannot be one p. The p orbital starts with second shell. Okay, so second shell has 2p, and this 2p will have three different orbitals in it. Okay, then you will have 3p, which will again have three different orbitals. 4p will also have three different orbitals, and so on and so forth. Okay, so unlike 2s, which had only one orbital, 2p will have three different orbitals in it. That is, electrons will have three places. Okay, all right, in 2p. Similarly, in 3p, it will have three different places where it can stay. Okay, and we know that each orbital can occupy a maximum of 2 electrons. That means 2p can have one electron here, one electron here, so that is 2 electrons maximum over here. Again, in this block, it can have, you can say, 2 electrons, and furthermore 2 electrons over here. So in all, 2 plus 2 plus 2, that is 6 electrons can be occupied in 2p. Similarly, for 3p, there can be a maximum of 6 electrons. Similarly for 4p. All right, so they are degenerate. Okay, so all these three orbitals, the one represented by -1, the one with 0, and +1, they all have same energy. Okay, that is why they are called degenerate orbitals. So all these three have same energy. So how do we know the difference between them? We'll see later on that from energy point of view, they seem to have the same value, so we cannot actually differentiate between them, but in presence of electric and magnetic field, we can see the difference between these three orbitals of 2p. Okay, and that is how we differentiate in them, and using those studies in electrical and magnetic fields, we can analyze their spatial orientations and how they differ from each other. So these three different orientations in every p orbital are represented by px, py and pz. Why is it so? We'll just see the diagram itself. Okay, so see here, you know that the shape of the p orbital is it is a dumbbell shape, that is it has two lobes. So it has two lobes. All right, so in px, okay, these lobes are aligned along the x-axis. Okay, that is to say, let's say this is your diagram, this is y, this is z. Okay, so the lobes here are aligned along the x-axis, so there are no electron cloud density along yz plane. Okay, the electron cloud density is entirely aligned along the x-axis, that is why we call it px. Okay, so you can say px has a value of -1. all right, then similarly, if the electron cloud density is aligned along the y-axis, we call it py. Let's say it has an m value of +1. okay, and in pz, the electron cloud density is aligned entirely along the z-axis. Okay, so this is pz, which means it will have m value of 0. Okay, so these three p orbitals are aligned along the three perpendicular axes which you know of. Okay, and that is why we can say that they differ from each other. So though, for example, for 2p, all right, so energy of 2px, okay, will be equal to energy of 2py will be equal to energy of 2pz. That is why they are degenerate, but their spatial orientation or their alignment is different. All right, and that is why we have three different m values. So which m value is assigned to which alignment or which orientation? So there is no fixed rule to it. Okay, you can say that px has, instead of -1, you can say it has a +1, okay, m value, and py, you can say instead of +1 it has a -1 m value. All right, but usually pz is assigned a value of m equals to 0. Okay, so they are all interchangeable, it doesn't matter. Okay, but you just have to remember that px means the alignment is along x-axis. Now see, once you have started with 2p, all right, then even the third shell 3 can have L value 1, that is there can be 3p, 4p, 5p and so on. Alright, so what is the difference? Again, the shape of 2p, 3p, 4p, they are all similar to each other. The difference is again of size. So in 2p, the electron cloud density is nearer to origin, that is the nucleus. The origin here represents, you can say, nucleus for now. Okay, so in 3p, the electron cloud density will even be further away from the nucleus. That is the extent of the lobe. Let's see if this is the py lobe, okay, or py orbital. So the extent of the lobe for 2p is this, then for 3p it will be a bit farther away. Okay, for 4p it will even be farther. See, the actual electron can be present anywhere from 0 to infinity, okay, in this lobe, but the likelihood, okay, the likelihood is represented by this shape. That means the likelihood of finding the electron for 3p is a bit farther away than the likelihood of finding the electron of 2p. Alright, even the 2p electron can go and reside very far away. Okay, it doesn't have to be necessarily very near nucleus, but the probability of it being near nucleus is more in comparison to that of an electron present in 3p or 4p or 5p. So once again, there is difference in size of the lobes, or you can say size of the orbitals, and there is also going to be a difference in the energy value. Next you have d orbital. See, the shapes keep on getting complicated. Okay, so they will be more complex, but you have to remember them anyway. So we'll just try and understand and memorize those shapes over here. So again, we have in d orbitals, we have degenerate orbitals. So d starts from shell number 3, okay, up to n equals to 1 and n equals to 2. Okay, so up to 2 there is no d orbital. Okay, for 1 there is only 1s, for 2 you have both 2s and 2p, and from 3 d orbitals come into picture, that is the L value of 2 comes into picture. Okay, so 3D will have 5 different m values. So m value can be 0, -1, -2, +1 and +2. Okay, because L is 2. Alright, so m can go from -2 to +2. So that means you will have 5 different orbitals present for any d orbital. Okay, so electron can have 5 different places or 5 different, you can say, homes where it can stay, and all these 5, okay, orbitals have same energy. That is why they are called degenerate. So how do they differ? Once again, they differ in terms of their spatial orientation or their alignment in 3D space. So let's look at those alignments. So we just saw that they have double dumbbell shape. Alright, so that is they have 4 lobes. So these are the 5 different orientations. One by one, let's look at them. So one we have is DYZ. So what is DYZ? In this, the electron cloud density is present along the YZ plane. Okay, it is present in the YZ plane. So the figure is actually quite self-explanatory. You can analyze it from there. Alright, so this is the YZ plane. So this is where the lobe is. Alright, in this YZ plane, and the XZ plane, along the XZ plane, there is no electron cloud density. Okay, you have to visualize it in space. Okay, so whereas in DXZ, the electron cloud density is along the XZ plane, or you can say it is between the X and Z axis. Alright, so see, if this is your X axis and this is Y axis, so in DXY the electron cloud density will be between X and Y axis over here. Alright, and whereas along the Z axis you don't actually have electron cloud density. So the plane, alright, if this slide, okay, this your computer screen is the XY plane, then the plane perpendicular to this XY plane, that is the one cutting through your screen of the computer, is the YZ plane. Alright, and XZ plane. So these two planes don't have electron cloud density over here. It is entirely present between X and Y axis for DXY. For DXZ, it is entirely present in, okay, across XZ plane, that is between the axis X and Z, and for DYZ it is present between axis Y and Z. So that is how you can remember their shapes. Alright, or if you remember the shape, you can remember their names or recall their names looking at their shapes. Alright, so these 3 are the 3 different orientations. Next is dx2 minus y2. Okay, so in this case it is a little bit different. Now see, here again you have X and Y, so the electron cloud density is going to be along XY plane. Okay, it is not going to be in XZ or along XZ or YZ plane. Alright, but the orientation is little bit different than DXY. In DXY, the electron cloud density was present in between the axis, that is, this is the X axis, this is the Y axis. So in DXY, the electron cloud density is present over here. Alright, between these two axes. In dx2 minus y2, the electron cloud density is present along the axis itself. So this is X axis, alright, and this is your Y axis. So it is present along the axis itself. Okay, so along X axis and along Y axis. Alright, that is, you can say it is centered around the X and Y axis. So that is the difference between dx2 minus y2 and dxy, but they still lie in the xy plane. See, when I am talking about that the electron cloud density lies along the plane, that means it is centered, okay, along that plane. Its shape is centered along that xy plane. It doesn't mean that the figure is a 2D figure. Okay, it doesn't mean that the electron cloud shape is a 2D shape. Okay, everything is happening in 3D. That is why it's difficult to comprehend. So see, for example, in this figure which we have shown over here in dx2 minus y2, along this axis, okay, so this is your y-axis and this is your x-axis. Alright, so the plane is a 2D plane, but the electron cloud density is in 3D. Alright, that is, it rises above this plane and below this plane as well. Okay, so it rises above xy plane and below xy plane as well. Alright, but there is no electron cloud density perpendicular to these planes. So we'll later on look into exactly where there is no electron cloud density. Okay, in the next lecture we'll study that actually in a bit detail. Okay. So similarly, see, for dy, z, dxz, dxy, everything is happening in 3D. So when I look at dxz, alright, it doesn't mean that the electron cloud density is present in 2D xz plane. It is centered around that plane. Alright, so it is on both the sides of this plane. Alright, the lobes are 3D lobes. Okay, so electron roams around in 3D region, not 2D region. Lastly, there is dz2. Okay, so dz2 has a unique shape. It doesn't have a double dumbbell shape. It has one dumbbell, okay, which is along the z-axis. That is why the name dz. All right, and dz2, apart from this dumbbell, okay, it's a bit different from pz. Okay, if it just had one dumbbell along the z-axis, it would have become pz orbital. Okay, it also has electron cloud density in a circular ring around the nucleus present in xy plane. Okay, so this is a bit more complex. All right, so you have a circular ring along the xy plane. So if this is your xy plane, then there is a circular hollow ring, sorry, not hollow, but you know, it's like a donut shaped ring. Okay, that is, it has a hole in between. All right, and then it has electron cloud density. Okay, so in this hole there is no electron cloud density. That is, the likelihood of finding electron is not there. Okay, but after this the likelihood of finding electron is very high. So this ring is present in xy plane, but the lobe is around the z-axis. Okay, that is, it is perpendicular to the ring. All right, so that is the shape of dz2, and each of this has a different m value. So dz2 is usually assigned m value of 0. Rest you can assign as per your convenience. Okay, so we can say dyz has a m value of -2. This has a m value of -1. Okay, this has m value of +1. You can say this has m value of +2, or you can say it differently. Okay, you can say this has a m value of, instead of -2, you can say dyz has m value of +2 or something else. Okay, but usually dz2 is assigned m value of 0. Rest you can interchange as per your convenience. So this is all about the orbitals. Okay. What you just need to understand is all these are very tricky concepts, so don't really worry about them, because we don't have to know these shapes much any more than what we have already studied over here. Okay, so just remember these shapes, their name, and the m values. For m values you can actually derive very easily by yourself. You don't have to remember those values. For example, if L is equal to 1, then you know that m will have value from -1 to +1. If L is equal to 3, then m will have value from -3 to +3. Alright, so just remember this S, P and D, and after that you don't actually have to memorize them, but for these three you should know the shapes and the significance of those shapes. And do remember that those shapes are actually 3D shapes, and they indicate the region. Okay, they are the shapes of the regions where electron is present. Okay, they are not some solid shells. All right, so they are actually just made up of electron cloud density itself. And what is electron cloud density? It is just a region where electron is likely present. All right, for example, if say in your room, all right, you can be present you might be sitting on your chair, you might be sitting on your bed, you might be standing on the northeast, at the northeast corner, you might be standing in the balcony of your room. So if I represent all of these regions with dots, okay, I get approximately a shape, all right, of the 3D region where you are likely to be present. So just like that, these lobes are formed. Okay, you just mark all the places where electrons are present, and the shape that marking takes is the shape of your orbital. Alright, and it so happens that all the d orbitals have these kind of shapes, all the p orbitals have the other particular kind of shapes. Alright, so similarly over here in d orbital you can have 3D, 4D, 5D, so on. Only the difference is that the size keeps on increasing. Okay, so the 5D orbitals have greater size than 4D, which have greater size than 3D. What do I mean by size? It means that the likelihood of finding electron is even further away from the nucleus. That is, you have to travel a little bit farther distance. Okay, a little bit of more distance. Okay, now in the next lecture we'll look at something called nodes, and how do we decide what nodes are from the shapes of orbital. Okay, so until then, and once again, thanks for watching Edupedia World videos.